Hello and welcome back to the CCENT journey with me, Ryan. In this next section we're going to pick up what is a subnet mask. In our previous videos we had a discussion around classful networking and addressing. We said that there was no such thing as a subnet mask before CIDR introduction in 1993. We said that the first couple of bits, which are called the most significant bits, located in the first octet, were used to identify which class the network was a part of, and in turn there was a standard dividing line between the network and host bits. In this video we'll take a look at how this is achieved but using a subnet and not the identifying bits, and why we needed to move away from the classful ranges into this new subnet mask and into the new classless domain. Along with this we're going to look at how we would interpret a subnet mask both as a dotted decimal value and as a network prefix, and then lastly we'll look at some subnet examples. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So before we dive into subnet mask and classless interdomain routing, I just want to hammer down the point of the problem with classful. So we've got a network here. Let's say our WAN provider gave us a public IP of 195.0.1.0. We know, looking at the first octet, this is actually a class C, and because it's a class C we also know that the first three octets are going to be for the network portion and the last octet is going to be for the host portion. So what we've done then was, on the back of this, was assign these IPs to our network. So this particular router here, let's say, got 195.0.1.1. This one down here got 195.0.1.2, and then we had .3 all the way up to, let's say, .100, all being used for our PCs over here. So we had a lot of IPs being used, but remember, in a class C there were 254 usable and we were only using 100 of them, so we still had 154 left over. Let's say, for example, for whatever reason we needed to split this network up because the broadcast domain was having too much chatter, or let's say we had to have another part of our network put aside for public access, as in maybe we want to put our servers there, or something like we obtained another company. So for whatever reason we needed to essentially have a different network. Okay, so now I modified the network. You can see that I've added this new section. Now because it connects off to the back of a router here, it's considered a different network, so it needs a different IP range and it's in a different broadcast domain. Now for those who don't know what a broadcast domain is, we'll come into that a bit later when we get to our Ethernet section. But essentially, because it's a different part of the network, it needs a different IP range. Now even though we have 154 IPs left down here, we can't utilize them, and the reason being the 195.0.1.0, these three octets were taken. No one else can use them, not even us, on a different network, because when a packet would come in destined for, let's say, 195.0.1.3 over here, if it was configured in two locations, this router here wouldn't know where to pass it. So because of that, we need a unique IP range for here. So what we would need to do at this point is actually go to our ISP, our service provider, and ask for another class C range. And sure enough, if we pay them enough money, they'll give us another IP range. Let's say they give us 197.5.4.0, and then we can use this IP range to assign inside this network. But what we've noticed here is we've wasted 154 IPs here, and we're going to waste a lot more IPs in this network. So to get around this problem of having these IPs wasted, we came up with this concept of taking away these classes, taking away class A, B and C, and having a different method to identify where the network and host portions begins and ends. And because we have this new method, what we're able to do is something similar to this. You can see that we have the 195.0.1.0 network that our ISP originally gave us, but what we can do is have anything from 0 to, let's say, 127 to be in this original large network, and then we can have anything from 128, so picking up where this one left off, up to, let's say, 36 for this network, And what we can do here is create small networks. So we can essentially what we call subnet this network down into smaller networks to accommodate, and in turn we would waste less addresses. So as time moved on, it was clear we needed a better way to break up the Classful ranges into much smaller blocks. So a subnet mask was introduced to help identify the dividing line between the network and host bits. So no longer would it just be a 130 is a class A, therefore the first 8 bits is the network. Engineers could now further subdivide that block into smaller blocks. This technique was called subnetting. So previously we said if you were given a 192, we know that this was going to be a class C. So previously we would say 192.168.0.0, we would say this was the network portion and this was the host portion. Well, what engineers can actually do was take bits, because remember there's 8 bits here inside this host portion, and move a bit into the network portion, allowing the engineer to have more networks but for the sacrifice of less hosts. And essentially this is the key or the idea around subnetting. What it also done was it got rid of this classful boundary. So for example, let's say we were giving this particular class C range, it doesn't mean that we've always got 254 IPs in that range. In fact, what we can do is break it up so we can have 2 ranges of 128 IPs each, or we can have 4 IP ranges with 64 IPs each. Using this subnetting technique allowed us to make better use of the IPs that were given to us by our supplier. Okay, so the other thing to pick up is there is a default subnet mask for the classful ranges, because remember at the time when subnet masks were released, there were still networks out there utilizing classful addressing. So to make things a little bit simpler, they gave a default subnet mask to each class. So they gave class A 255.0.0.0, class B 255.255.0.0, and class C 255.255.255.0. Now the 255, as far as the default classful ranges are concerned, would equal the network portion, and the zeros equaled the host portion. So just like before, with a class A, only the first octet was the network, and the remaining 3 octets were the host. And for class C, the 3 octets at the beginning were used for the network, and only the last octet was used for host. I've also put here a /8, /16, and /24. This is referred to as the slash notation, also sometimes called the CIDR notation, and sometimes called the network prefix. And when we get into understanding subnet mask in a bit more detail, these will come quite clear to you. But essentially it's a different method to represent the subnet mask. So representing a subnet mask. A subnet mask purpose is to inform the host networking device, whether that's firewall, router or PC, how to calculate its network address. Now a few things to know about a subnet mask on how it's kind of represented and some importance around the binary and decimal elements. First of all, a subnet mask is 32 bits long, just like an IP address. A subnet mask can either be off or on. Remember, anything in binary, same with an IP address, can either be off or on. If it's on, as in it's a 1, it represents the network portion, and if it's a 0, it represents the host portion. Now if we take, for example, our decimal format of a class A, which we know was 255.0.0.0, and we know that the 255 element is the network portion and the 3 zeros are the host portion. So why is 255 the network portion and the zeros are the host portion? And that doesn't come clear until we look at it in binary. You'll notice in binary, having all the ones turned on in the first octet equals 255 in decimal. And you can see the 3 host octets are all set to 0. And the reason they're host is because, like we said on this second bullet point here, we said 1 represents the network piece, so the first 8 bits are for the network, and we said 0 represents the host, so that means the remaining 3 octets are for the host. The last point is a subnet mask gives us the ability to determine the line between the host and network which may sit inside an octet. So what we mean by this is initially lean on to bullet point 3 and 4 where we had this decimal format and we converted it into binary. if we need to change what bits are the network and what bits are the host, that would have to be done in binary. And the reason for that is because if I give you something like 255.255.255, you can't split 255 in the middle because it's a decimal number. So when we convert it to binary, what we can do is decide what bits we want off and on. So an example of that is I've put together this chart, and we can see that in this particular octet we have all the bits turned on, therefore it equals 255. In this octet we decided to only turn on the first bit, and that left us 7 bits turned off, and in binary the first one's 128, so 1 bit on is 128. Here we've got the first 3 bits turned on and the remaining bits turned off, and that equals 224. The reason being is because the first bit here is 128, the next bit is 64, the next bit is 32, and if you add up all 3 numbers it equals 224. So in order to actually subnet, we need to understand it at a binary level, because at binary is where we can turn the bits into host or network bits by turning it on or off. For example, if we look at a class C in binary, we know it's 255, 255, 2550. It will look something like this: 1, 1, 1, 1, 1, 1, 1, 1. So that's 8 ones, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Dot 0, 0, 0, 0, 0, 0, 0, 0. So it's 8 zeros, which are the host portions, and 24 bits turned on, which is the network portion. Well, in binary what we can do is we can decide to turn on more bits in this host portion and therefore create a different subnet mask. And creating a different subnet mask allows us to have a different value of host bits as compared with the new network bits. And this is the first step of subnetting. Okay, so let's start with an example so you can see what I'm referring to here. Let's say we were giving this particular subnet mask. We can see that the first 3 octets are all 255, 255, 2550, and this is our network portion, and the last octet is our host portion. In binary, we know that 255 are all the bits turned on, so that means that there are in total 24 bits turned on, and that left us 8 bits turned off because a subnet mask is 32 bits long. Now we decided that we don't need this many host bits. In fact, what we'd rather do is split those host bits up and give them to the network portion. So the way we do that is, you can see here, we don't need that many host bits, so we move the host bits into the network bits, and now we have 2 additional network bits. If we were to convert this into decimal, we would again have 255, 255, 255, but in the last octet we have 192. And the reason we have 192 is because if we took these 8 bits and we put them into decimal, and in order to do that we need to bring up the decimal to binary format table that we discussed in the last video. We can see that we have the first 2 on and the rest turned off, and if we add up the 2 values that we've got turned on, so it's 128 plus 64 equals 192. Hence why in decimal this is 192. However, because now we've finished and we've given them 2 network bits, we leave the rest of the bits turned off, and these are now our new host bits. So we've got less hosts, but we've got more networks. Now also keep in mind that before we had 24 bits turned on, now we have 26 bits turned on. So this is why the CIDR notation or slash notation or network prefix was a /24 and now it's a 26. So using our example at the bottom here, you can see that we have the network portion, we have the new bits that we've turned on, which we're going to refer to as the subnet ID, and then we also have all these zeros, which we know is the host portion. So keeping that in mind, let's have a look at these formulas. So to figure out the number of subnets, we need to do 2 to n, where n is the ones in the subnet ID. So in this case, we need to go 2, we need it 2 times, so that's 4, right? So it's 2, 4. So we have 4 new networks, okay? By turning on these 2 bits, we have 4 new networks. Now, how many hosts are in each network? We figure out that by doing the next formula, which is, again, 2 to the power of n minus 2. And the reason we minus 2 is because we have the network and the broadcast address. So, again, all the host IDs. So here we have 1, 2, 3, 4, 5, 6. So that's 2, 4, 8, 16, 32, 64. 1, 2, 3, 4, 5, 6. So that means that we have 4 networks, and in each network there's 64 available hosts. But we also need to minus 2, so that means there's 62 available hosts. And the reason for that is because in each network there's a network address and a broadcast address. And we'll get into that in a moment and explain in a bit of detail what they actually mean. Okay, so now we've seen a very brief example of the technique around subnetting, and I appreciate it's only been one example, so we're going to get into more examples as the video series continues. I want to go back to the big picture and tackle what we've learned today against this existing network. So let's say our ISP gave us 82.100.90.0/24. Now the first things first is we're talking here classless and not classful. If we were talking classful, we would look at the first octet and say this is a class A, and because it's a class A, the first octet is the network portion and the following 3 octets is the host portion. However, that's not the case. We're dealing with classless, and because we're dealing with classless, it's not the network and identification bits that determine the network and host portion of the IP address, but it's actually the subnet mask. Now, the subnet mask that we've been given from our supplier is a /24, which is the subnet mask but presented in what we call a CIDR notation, sometimes called a network prefix. And essentially this means how many bits of the available 32 bits are turned on. And remember, those on bits represent our network. So first things first, let's figure out the subnet mask of the /24 that we were given from our supplier. In order to do that, we need to turn on 24 out of the 32 available bits. So going from left to right, let's turn them on. 1, 2, 3, 4, 5, 6, 7, 8. Dot. 1, 2, 3, 4, 5, 6, 7, 8. Dot. 1, 2, 3, 4, 5, 6, 7, 8. Dot. So that's 8, 16, 24. And then the remaining bits, because now we've got this, are all turned off. And because it's 32 in total, take away 24, leaves 8. So 1, 2, 3, 4, 5, 6, 7, 8. So there's our host portions. So this is actually our host, and all of these here is actually our network. So by default, without any subnetting, how big is the network that we've been given from our supplier? And again, we use that formula, which is 2 to n minus 2 on the amount of bits that are turned off. So there are 8 bits turned off, which means it's 2, 4, 8, 16, 32, 64, 128, 256. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 bits turned off. 2 to the power of how many bits turned off is 256. But remember, we need to minus 2 because of that network and broadcast, which I'll come back to in a moment, which gives us 254 usable IP addresses. However, even though that's great, we've got 254 usable IPs, what it doesn't do is it doesn't hit what we need here, because what we actually do need is 2 networks and not 1 network. Because if you remember previously, we've got a network here, also referred to as a broadcast domain, and we have a network here, also referred to as a broadcast domain. And we can't have 1 network to satisfy, or 1 IP range to satisfy these 2 networks. What we need to do is subnet this down, so we have some IPs here and some IPs in here. So the way we're going to do that is, first of all, we need to understand what's our requirement. Now we've got 2 options. We can either subnet based on host requirements, which is what we've done earlier, or we can subnet based on subnet requirements, which is what we're going to do here. So I'm not concerned about how many hosts are inside the range, but what I am concerned about is how many networks that gives us. And to make that a little bit more interesting, we're actually going to say that we have the total of, let's say, 9 networks. So we have 2 here, and we also have 3, 4, 5, 6, 7, 8, 9. So let's pretend that we have actually 9 networks. So that's 9 broadcast domain. Here's one, and then here's the rest of them down here, all right, off the screen. So we're going to just pretend we have 9 to give it a bit more of a challenge with the subnetting. So first of all, we need to figure out how many bits we need to sacrifice of our host portion to create 9 networks. Now, if we're trying to subnet based on host requirements, we go from right to left. And if we're subnetting based on network requirements, we go from left to right. In this case, because we're doing network, we're going to use the left to right. So, doing our powers of 2 from left to right, we've got 2, 4, 8, 16, 32, 64, 128, 256. Now, in order to have 9, we know that we're going to at least have to look at turning on 16. So we're going to turn on 16 and all the ones below that. Because 8 was too little, 32 is way too much, 16 is the lowest we can have turned on. That allows 9. So because of that, our new subnet mask is 4 ones and the rest is zeros. If we had to calculate the other way around, let's say we had a requirement where, similar to what we had previously in the video, where we had host requirements instead of subnet requirements, then we would do it the other way around. So for example, let's say we had a requirement of 33 hosts, then going from this time right to left, we're going to go 2, 4, 8, 16, 32, 64, 128, 256. Well, what we would need to do is have these bits turned off, and 32 is too small, and we'll turn on the bits once we've hit our requirement. So you can subnet from left to right for networks and from right to left for host. In this case, we're going to be doing it based on the subnet requirement as previously explained, so we're going to go from right to left. We've done that and we've come up with 16 being the smallest that we can have, and therefore we have to turn on all the bits that are left of 16, leaving all the bits right of 16 as our new host. Because of that, our new subnet mask would be like this: 1, 2, 3, 4, 5, 6, 7, 8, dot 1, 2, 3, 4, 5, 6, 7, 8, dot 1, 2, 3, 4, 5, 6, 7, 8, and then the 4 turned on, and then the 4 turned off. Now to figure out how many networks we have, we know that because 2 to the power of how many bits are turned on is 16. So that's 2, 4, 8, 16. And to figure out how many hosts per network, it's also quite easy because we need to do 2 to n minus 2, where n is the amount of bits that are turned off. So again, 2, 4, 8, 16 minus 2 means there are 14 usable addresses per the 16 networks that we've created. And 16 network is more than enough for this 9 network requirement. Okay, so just making a bit of space. It's getting a bit crazy here. So let's think about the CIDR notation and the decimal format of this new subnet that we've created. Now, thinking about the last octet, we turned on 4 bits and we left 4 bits turned off. Now, previously it was a /24 because 24 bits were turned on. Well, here we have 8, 16, 24, 25, 26, 27, 28. So it's a /28. Now, to work out the decimal, what we're going to do is write out our decimal conversion and place these binary bits under the correct values. So from left to right, we've got 1, 2, 3, 4, and then 4 zeros, 1, 2, 3, 4. All the bits that are turned on, if we add them all up, so that's 128 plus 64 plus 32 plus 16 is 240. So a decimal subnet mask in decimal format would be 255.255.240. Okay, so what have we actually achieved out of all of this hard work? Now, initially we had 82.190.0/24, which gave us 256 IPs in the host portion, 2 of which couldn't be used because 1 is the network and 1 is the broadcast. Now what we've done is we took those 256 IPs and we broke them down into 16 networks, with every network having 14 usable hosts. And the way that would write out now is here you can see I've popped 82.190.0, and that will go .1, .2, .3, .4, .5 all the way up to .15. Then the next network will start 82, 100, 90, 16 all the way up to 32, and the next network will start. But like I said, we lose 2 IP addresses. We lose one for the network and one for the broadcast. Now the first one of each range, so here is the .0, here it's the 16, and here it's the 32. These are our network addresses, and these can't be used by any host. You can see the first usable one is actually going to be .1. The second usable is .2. So those can be assigned to the host. Now the last one, which is 15, and the last one in this one, which is 31, is what we call the broadcast address. Now this 32 here I've stopped, but ultimately this pattern will continue all the way up to 254 being the last usable. So in the end you have 82.190.254. And then what we can do with this is take one of these networks that we created, and here we can say 82.190.1 is here. .2 is there. This PC can have .3, this guy can have .4, this guy can have .5, this guy can have .6. And then what we can do is get the next network, which starts with 16. Remember, 16 not being the first. Remember, 16 not being a usable address. Get 17 and give 17 to this guy, 18 to this guy, 19 up here. And what we've done is we've actually split what originally we had a /24 into multiple /28s. And actually we have 16 /28s that we've created. So just quickly, we're going to finish up on what is a network address and a broadcast address. So I said every time that we perform subnetting, essentially every network will require a network address and every network will require a broadcast address. So a network address essentially is what routers use to route towards. So for example, let's say that we had 82.150.0.0/24 here. This would be our network address, with .1 being the first usable, .2, .3 and so forth, all the way up to 255, but 255 would be our broadcast. So the last usable would be 254. Now the network address is what routers would actually route towards. So what I mean by that is it essentially represents the network that you're on, hence network address. So if we had a router over here and the router had a routing table, it wouldn't actually have 82.150.0.1/02.03 for every single host. In fact, all it would have is just this one entry, because routers route towards the network using the network address, and then once communication is happening inside the network, it then routes towards the host portion of that address. As for the broadcast address, which is the last address in the range, in this case would be 255, essentially that means that if you were to communicate with 82.150.0.255, it will go out to all hosts inside that network. So for example, let's say I'm on this PC and I'm .3 and I decide to send a ping to 82.150.0.255, then essentially what will happen is that ping will go to every single host that lives inside that network, and that is what we call a broadcast message. Any other IP that I try to ping, let's say I ping .2 or .100, providing they've been assigned to a host on the network, then that wouldn't be a broadcast communication, that would be a unicast communication, which is a one-to-one. Okay, so that's all we've got time for in this lesson, and if you carried on to the end, well done. It was obviously a longer than normal lesson. I appreciate that subnetting is not an easy thing to understand, and repetition is key when it comes to it. We're going to have the next couple of videos talking more about subnetting, the different types of subnetting that we can do, which is fixed length and variable length, and then we're going to go into lots of Q&As around sort of giving you some questions, some time to answer them, and then we'll go through the answers together. So what did we do in this video? We discussed what is a subnet mask. We said that back in the Classful days we used the networking bits to identify the network and host portion, but that wasn't going to sustain us moving forward, so we came up with a new method which utilizes this subnet mask to identify where the host and network portion starts and stops. We talked about why we needed to move away from Classful. We gave that example at the beginning where we had a particular network that was utilizing about 100 or so IPs, but there was still quite a few IPs left. But because we had a different network, we had to go to a provider and ask for another IP range. There was no possibility of actually splitting up that original Class C. So then we went into what is a subnet mask, how it represents and displayed. So we said that there are CIDR notations and the decimal format. Both mean the same thing, but they're presented in different ways. We said that if the bit is on, it represents a network, and if a bit is off, it represents the host. And we said in order to do subnetting, we had to translate it into its binary values and then turn the bits that we needed on or turn the bits that we needed off. We then went through an example of subnetting, only really one example to begin with, but like I said, we'll get into more examples as time goes on. We looked at the formulas that are used in subnetting, which was 2 to the power of n to work out the amount of networks, and then 2 to the power of n minus 2 to work out the number of hosts required. And then we finished with the big picture. Essentially, we got that production network that we had at the beginning, where we ran into problems with the Classful networks, and then we essentially broke it up into multiple /28s and assigned those 9 networks that we had as a requirement, each their own /28 that lived inside the /24 that was originally supplied to us from our ISP. I hope this video has been informative and I'd like to thank you for viewing, and if it has been, please do like and subscribe.